So we're going to talk about what we refer to as the simple gas laws. You should have learned about these in your previous chemistry class. There are four basic variables when we talk about gases, and those are pressure, abbreviated with a capital P, volume is capital V, temperature, capital T, and we measure the amount of the gas in moles, and that's given the letter N. We've already used M for so many other things, we couldn't do that. Those properties are interrelated. If you change one, it's going to affect the others. And the simple gas laws look at the relationships between pairs of these variables. So looking at the relationship between pressure and volume, or between pressure and amount of gas, just looking at two. So Boyle's law. Robert Boyle lived in the 1600s. This research was very, very low tech. There was no such thing as tech. And he studied the relationship between the volume and the pressure of a gas. Now, I'm going to mention these guys' names, and the dates are up there. I'm not going to test you on that. This is kind of backgroundy stuff. So he took a J-shaped tube and put some mercury in it. And now he's got a stopper here, and there's some gas trapped in here. Is the gas in here at a higher pressure or a lower pressure than the atmosphere? It's higher because it's pushing the mercury down. The atmosphere is pushing down this way, and this gas is pushing down that way, and the gas is winning. So he looked at that, and he could figure out what the volume of that gas is, and the pressure, by looking at this height, told him the difference between that and the atmosphere. Then took some more mercury and poured it into this tube. So the mercury level went up here, and it also went up here, and it squished that gas into a smaller volume. He can still measure the pressure, though. The pressure difference is related to this height difference. So now the pressure in here is greater than it was before. Atmospheric pressure hasn't changed in doing this. And so we see that the pressure went from this to this, the pressure increased, the volume got smaller. Which makes sense. If you squish a gas, if you put pressure on it, it'll compress and get smaller. This is what's known as an inverse relationship. When one quantity gets bigger, you increase the pressure, the other quantity gets smaller. The volume gets smaller. So scientists like to graph things because it helps us to have a visual picture of what's going on. So we can look at the volume of the gas as a function of the pressure. So measuring the volume as we change the pressure. As the pressure increases, the volume decreases. And we see this sort of exponential curve here. So that's all nice, but straight lines are better. So if we graph this a different way, we can make it into a straight line. I'm going to skip ahead to this one. I'll come back to the other one. So here's volume versus pressure. If instead we graph volume versus 1 divided by the pressure, the inverse of the pressure, then we get this really nice straight line. And this tells us that the volume is proportional to 1 over the pressure. That's a linear relationship. So Boyle's law can be expressed this way. Volume is proportional to 1 over the pressure. This is at constant temperature and constant amount of gas. Because if you're going to look at these two variables, you have to keep the others constant. So you can express this in different ways. It comes down to that the pressure times the volume for a particular sample is going to equal a constant. And so the pressure times the volume under one set of conditions will equal the pressure times the volume under the other set of conditions. And this is what we refer to as Boyle's law. And that's the form that we use to solve problems. P1V1 equals P2V2. Well, it's a lot like M1V1 equals M2V2, but here we're talking about gases, not dilution. We can look at an interpretation of Boyle's law on the molecular level. Here we have a piston assembly. This is a container where we can change the size of the container so this lid can go up and down. Here we've got a 1 kilogram weight sitting on it, and here we have a pressure gauge that's telling us that the pressure in there is 1 atmosphere. If we double the weight on here, well, we can cut the volume in half, and we can see that the pressure doubles. So the volume went down by a factor of 2, the pressure went up by a factor of 2. It makes sense that the pressure is higher because we have the same number of particles, but now they're occupying a smaller amount of space. When I look at this, I think of kindergartners running around in a classroom because the teacher had to step out for a minute, right? So here you've got 2, 4, 6, here you've got 10 kindergartners in a room. They're running around. They're going to run into each other. They're going to run into the walls. If we put them in a room that's half the size, they're going to run into things more often if they keep running at the same speed. Does that make sense? More collisions, more pressure. These pressure concepts have a lot to do with scuba diving as well. You've probably experienced the sensation of when you go underwater, you begin to feel pressure on your ears. That's because as you go underwater, the pressure increases much faster than it does just, going down in altitude, because water exerts a lot of pressure. For every 10 meters of depth that you go underwater, you're going to experience an additional atmosphere of pressure. That might not sound like a lot, but the pressure's doubling, right? It's twice as much. So at 20 meters, you're going to experience approximately 3 atmospheres of pressure. So up here, 0 meters, 1 atmosphere. Every meter that you go down increases 1 atmosphere. So at 10 meters, it's 2 atmospheres. At 20 meters, it's 3 atmospheres. If you hold your breath, if you've been down deep underwater and you hold your breath and you come to the surface quickly, let's say you were down 20 meters, then the pressure is going to go from 3 atmospheres to 1 atmosphere, and if you're holding your breath, the pressure of the gas in your lungs was at 3 atmospheres down there. And now the external pressure is only 1 atmosphere. That's going to cause a large expansion and can cause a lot of damage to your internal organs. There's a reason that you have to take a whole bunch of classes and get certified before they let you go scuba diving. Because you can kill yourself very easily by doing something that would seem okay. It's very important to exhale while you're rising because you need the pressure in your lungs to equalize as the pressure outside is changing. I'm not going to test you on scuba diving stuff. Okay, so here we have a question, and this is kind of a difficult one. It's kind of a tricky one. This is what's in the book, and it's what I decided to do. So we're going to do it. So let's read all the words. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? Okay, this one is kind of tricky. It's not really very straightforward. Sometimes we need to draw some pictures. Even if they're ugly, they can help us figure out what all those words mean. So here we have the surface of the water. And we've got a syringe. So here's the syringe. And the volume there is 16 milliliters. So we'll say, well, this one's pretty full. Okay, so 16 milliliters. Got a bunch of air in it, right? And then we're going to go down, take it down below the surface. So down here somewhere. The pressure down here is greater. So In this syringe, there's a pressure of the gas inside because it's sealed off at this end. And then there's this plunger, right? So here the pressure inside is equal to the pressure outside, 1 atmosphere. When we go down here, the pressure increases. That's putting pressure on the plunger. So it's like you putting your thumb on it and pushing it in, right? So this gets pushed in. The volume down here is 7.5 milliliters. So I'm just trying to draw pictures to show what these words are saying. It says that the pressure at the surface is 1 atmosphere. So it's 1 atmosphere up here. And it's asking the first question, what's the pressure at this depth? So down here, what's the pressure? Okay? So I have 2 volumes and I have 2 pressures. So I can use Boyle's law. P1 V1 equals P2 V2. Well, let's label these. Let's maybe call these 1. So this would be pressure 1 and volume 1. So call this pressure 1 and volume 1. Those will go together. They're occurring in the same time. And then down here, this is the other one. So this is volume 2, and this is going to be pressure 2. Okay? So we have an equation here, and we need to rearrange the equation and solve for the thing that's missing here, P2. It's always best to rearrange the equation before you stick the numbers in it. So I want to isolate V2. I'm going to do that, dividing by P2 on both sides. The P2's cancel out, and I get V2 by itself. So V2 equals P1 V1 over P2. There are a lot of letters and numbers here, and it's easy to mix them up. So write them out clearly, and then go back and look and make sure that you copied them down right. So I need pressure 1, so I'm going to go over here. This is 1 atmosphere. And volume 1 was 16 milliliters. And then I'm going to divide by, you see what I did there? Yeah, that's what you guys are mumbling about. I'm not trying to solve for V2. I'm solving for P2. Okay, P2, I need to divide both sides by V2. So P2 equals P1 over V1 over V2. Which, you know, I realized when I got here that, oh, wait a minute, that's not going to work. It's okay. We all make mistakes. So volume 2, 7.5 milliliters. Always write the units in. What happens to those units? The milliliters cancel out. So we don't need to convert anything there. I've got 1 times 16 divided by 7.5. So pressure 2 equals 2.133 repeating atmospheres. By rules of sig figs, this should be 2.1 atmospheres, just 2 sig figs. So that's the pressure at that depth. Any questions? Now the next question in here is a little trickier. This is, requires a little bit of critical thinking and problem solving. If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So what this is saying is I go down 10 meters, I add 1 atmosphere. If I go down another 10 meters, I add another atmosphere. So down here, it's 2.1 atmospheres. At the surface, it was 1 atmosphere. What is the increase in the pressure? Well, it'll be the pressure down there minus the pressure at the top. So the pressure has increased 1.1 atmospheres. I get an increase of 1 atmosphere for every 10 meters. That's a conversion factor. 1 atmosphere per 10 meters. So I could take this number of atmospheres and multiply by 10 meters over 1 atmosphere, and that's going to give me 11 meters. The syringe is 11 meters deep. That's tricky because you can't just take the 2.1 and convert it. That would give you 21 meters. Well, that would be true if pressure at the surface was 0, but it's not. Any questions? Charles' law. So Charles lived in the 17 and 1800s. He looked at the relationship of gases in terms of the volume and the temperature of the gas. So he found that the volume of a gas is directly proportional to its absolute temperature. So we can also express that as the volume divided by the temperature is equal to a constant. Or we can express it this way, V1 over T1 equals V2 over T2. Now, it's important here that this be the absolute temperature. Absolute temperature is the temperature in kelvins. Okay? The temperature for gas problems must always be expressed in kelvins. They will give you the temperature in Celsius most of the time. They will ask you to find a temperature in Celsius, but in the equation you have to use kelvins. No exceptions. Let's look at why. So here's a graph of gas volume as a function of temperature. So here we have different amounts of gases, but for each amount we see that the volume is proportional to the temperature. So we get nice straight lines here. So this was done down to 0 degrees Celsius, which is, you could do that easily by putting it in an ice bath and using higher temperatures than that. We get this nice straight line. If we extrapolate the line, go past the actual data, and do that for all 3 lines, what we find is that they intersect at this point down here. That would correspond to a temperature of minus 273.15 degrees Celsius. And that would also be the point at which the volume of a gas was 0. So that is the theoretically lowest possible temperature. 0 temperature, 0 Fahrenheit, 0 Celsius, you can go below that, right? Absolute 0, you can't go below that. So the Kelvin scale has no negative temperatures, and it never has 0. If you look at this equation, we've got temperature in the denominator here. What happens if you divide by 0? It's undefined. You can't divide by 0. This equation will not work if we have any zeros. And it's not going to work with the Kelvin scale anyway because, well, just because. So we have to use kelvins, the absolute temperature. So let's look at a molecular view. What are the molecules doing? So this is something you can try at home. Blow up a balloon and put it in ice water and watch it shrink. So you've cooled it down, lowered the temperature, the volume goes down as well. Put it in boiling water, heat it up, the temperature gets bigger. Depending on how much air you put in there to start with, it could pop. So if you don't like that, I don't like being surprised by things popping, then don't fill it up too much. Why is the volume of the gas changing? Well, the pressure from the atmosphere on each of these balloons is the same. The amount of gas in there is the same. When the temperature changes, temperature is a measure of the average kinetic energy of something, the energy of motion. So here we have particles at a high temperature are moving faster than they are at a low temperature. So think about the kindergartners again. If you have kindergartners and you gave them all rock stars for lunch, right, that would really be ugly. They would be running faster, right? When they run faster, they're going to run into each other and run into the walls more frequently, right? So if you want to maintain the same amount of pressure, you're going to have to give them a larger space to run around in. The balloon expands because the pressure on the outside is going to be the same as the pressure on the inside. The balloon allows it to expand. If we didn't allow it to expand, then the pressure would go up. Any questions about that? A lot of these gas laws we can reason out by thinking about, what do balloons do? So the temperature of gas increases, particles move faster. They collide with the walls more frequently and with more force. And so if we want the pressure to remain equal, we have to let the gas expand in volume. I remember being fascinated by hot air balloons as a kid. Gee, on the cartoons, they blow balloons up and then they float, right? And that doesn't happen in real life because, cartoons are just a study in breaking the laws of physics. So we understand that a helium balloon will float, but we also understand that if you put a hole in a balloon, it goes flat, right? So here we have hot air balloons. They're not helium, and they've got a big hole in the bottom, and yet they'll lift people off the ground, right? Crazy. What's going on there? Well, there's this ginormous burner here, and it's heating the air. And when you heat the air, what happens to it? It expands. The volume increases. Well, if the volume changes, does the density of the gas change? Yeah, it does. So let's remember, density is the mass of the gas divided by the volume. So that air, the mass hasn't changed, but the volume has gotten much larger, right? So that means the density of the gas is lower. So the density of the hot gas inside this balloon is lower than the density of the cold air outside. Less dense things float. And so this balloon is floating because the air is warm and less dense. And so you can control it going up and down by changing the temperature of it using this big old burner in here. There's a picture of a shriveled up balloon in some liquid nitrogen. You can't do that one at home. Okay, let's do a problem here. Charles' law. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? Okay, this is a more straightforward type problem. So in the last one, we drew a picture and we thought about it. Most of these problems, the better way to organize them is to make a chart, a graph. No, a table, that's what I meant. Make a table. So I'm going to make a table here. And I'm just going to write down the numbers as I come to them. So the first thing I come to is 88.2 milliliters. So I'm going to write that in here, 88.2 milliliters. And Is that pressure, volume, amount of gas, or temperature? It's not a trick question. It's volume, right? So this one says volume of. If it doesn't specifically say that, the unit will tell us this is a volume. So I'm going to label this column in my table volume. So volume of 88.2 milliliters, and we're heating the gas from 35 to 155. So it starts out at 88.2 and 35. So those two go together, so I want to put those together on the same row. This is a temperature, and it's going from 35 to 155. Is degrees Celsius a unit that we can use here? No, we have to convert this to kelvins. So the conversion is 273.15. Here we're using temperatures to the nearest 1 degree. It's okay to just round that to 273. If you want to use 273.15, that's better, but we're going to come up with the same answer. So 35 plus 273, 308 Kelvin. You want to convert the temperatures before you start doing anything else. As soon as you write them down, say, oh, it has to be in Kelvin. Let's fix that. Plus 273, 155 plus 273, 428. So this is one set of conditions. Those two went together. I'm going to call that 1, and I'm going to call the other one 2. I have an empty square rectangle in my table. I'm going to call that V2 because it's in column V and row 2. Okay, so I've got V1, I've got T1, I've got T2, and I'm looking for V2. What is the final volume? That's what it's asking me to find. So I need an equation with volumes and temperatures. That's going to be Charles' law. Charles' law is V1 over T1 equals V2 over T2. Now, like the density equation, anytime there's a fraction in the equation, especially if you're solving for something in the denominator, people do very bad things with algebra. Okay? So some of you are great with algebra, you're fine. A lot of you, though, I saw it on the exam, you did some crazy things with densities. So for those of you that struggle with algebra, what you want to do here is we want to get rid of the fractions before we try to solve this equation. So we're going to cross multiply. So cross multiply means I'm going to take the top of one side times the bottom of the other, and the bottom times the top. So I'm going to cross multiply. I'm going to get V1 times T2 is equal to T1 times V2. Okay? When we get rid of the fractions, then we're more successful rearranging the equation. Because I'm looking for V2. Here's V2. So divide by T1. So V2, that's what I'm trying to find, is equal to V1 times T2 divided by T1. This is not the only way to solve these problems, but for students that do not intuitively understand this, this seems to work the best, and so that's why I'm teaching it this way. Any questions about the equation? You really should show your work when you do these problems. You don't necessarily have to show this part, but you should show the rearranged equation with variables, and then we should show it with the numbers plugged in. So now I'm going to take volume 1, 88.2 milliliters. Always write the units in here. I'm going to take temperature 2, 428 Kelvin, and then I'm going to divide by temperature 1, 308 Kelvin. We'll see that the kelvins cancel out, so that's a good sign. 88.2 times 428 divided by 308, 122.56, and the unit is milliliters. Notice when I started, I had 35 degrees Celsius. That has two significant figures, but when I convert it to Kelvin, because I'm adding, now it's got 3 sig figs. So 3 sig figs, 3 sig figs, 3 sig figs, so this should have 3. So 123 milliliters is our new volume. With these simple gas laws, you should be able to look at that answer and ask yourself, well, is that reasonable? So I took the gas and I heated it up. If I heat up a balloon, is it going to get bigger or smaller? It's going to get bigger. The volume got larger. That's a good sign. Doesn't prove that I did it correctly, but it's a good sign. If you get things backwards, it might get smaller, and then you'll go, oh, wait a minute, that's wrong. Any questions? Avogadro's law, relationship between moles and volume. So you probably remember the name Avogadro from Avogadro's number. Amadeo Avogadro, born in 1776. He was the first one to state formally the relationship between the volume of a gas and the amount of gas in moles. It turns out that the volume of a gas is proportional to the number of gas particles, not their mass, not their size. And so this makes gases very different from liquids and solids. It's the number of particles. So Avogadro's law says that the volume of a gas is proportional to the amount of gas in moles. And this is assuming constant temperature and pressure. So we typically express it this way: V1 over N1 equals V2 over N2. We count the number of gas molecules using the unit mole. And so equal volumes of equal gases have equal numbers of molecules, have equal moles of molecules. What the gas is doesn't matter. We'll talk more about that later. So here's a graph of some data demonstrating Avogadro's law. Here's the volume of the gas and the number of moles. As we increase the amount of gas, the volume goes up. That makes sense. Think about a balloon. You put some air in the balloon, and you put some more air in the balloon, and it gets bigger, right? The more air you put in, the bigger it gets. If we take this and extrapolate to 0, we'll find that this predicts that 0 moles of gas would occupy 0 volume. Well, that makes sense. Okay, lots of words in these problems. A chemical reaction occurring in a cylinder equipped with a movable piston, there's a lot of movable pistons in this chapter, produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? Assume constant pressure and temperatures and that the initial volume amount of gas completely reacts. Okay, so what do we do with this? Well, let's make a table. Let's make a table and collect numbers. So here's my table. The first number given is 0.621 moles. Okay, moles. That's the amount of the gas, and we use the letter N as the variable. So that's N. 0.621. So it produces that. If the cylinder contained 0.12 moles of gas before, well, So there's another mole. I better put that down here, 0.120 moles. And had an initial volume, 2.18 liters. So this 0.12 moles goes with the 2.18 liters. Do you see that? So I want to put the 2.18 liters on the same in the same row as this. These two go together. It doesn't matter if you call them 1 or 2, but they need to be paired up the right way. So this one was after, and this is the starting, the before. So if it bothers you that that's on the bottom, we can call the bottom row 1 and the top row 2, if that makes you feel better. This column is V for volume. So I took the numbers and I organized them in a table. And then what's the question? What was its volume after the reaction? So this was the product, and it's asking me the volume that goes with that amount. So this is what I'm trying to find. So we could call that V2. Any questions? So I need Avogadro's law. V1 over N1 equals V2 over N2. We need to rearrange that. Okay, I showed you how to cross multiply and do all of that. Here's another thing you can do with simple fractions like this. So if I take the denominator here, I can move it to the numerator on the other side. I can take this one and move it up there. I could take this and bring it down here. You can go across the equal sign as long as you do it diagonally. Okay? So if I want V2 by itself, V2 is going to equal N2 times V1 over N1. I can take this from the bottom and put it up there. It's the same result as cross multiplying and then rearranging. It's just faster. If you need help rearranging equations, please ask me and I will go over it until you get it or you decide that you don't care. Whichever comes first. And then we'll just come back and try another day until you get it. So N2 is 0.621 moles and volume 1 is 2.18 liters. And I'm dividing by N1, 0.120 moles. This table really helps because it labels everything. And so when we go to fill these in, we know which number to pull. So look at the units, moles and moles. Those are going to cancel. So 0.621 times 2.18 divided by 0.12. So my calculator is telling me all of my numbers had 3 significant figures. So the volume is 11.3 liters. Yeah.
Did the initial 0.12 moles get reacted? Is that like
Yes.
part of it? Okay, so it's not there in the final.
Yeah, and I actually added a little to this because it didn't specify that in the textbook. And so I'm saying assume constant pressure and temperature and that the initial amount of gas completely reacts. That bothers me about this problem. Because, yeah, you started with this amount of gas, but if it didn't all react, then you can't do the problem. So, very good question. So we've got more gas at the end than we did before, so we expect that this volume is larger, and it is. So there we go. Any questions? Oh, shoot, another one. Okay, do this one too. Scale model of a blimp rises when it's filled with helium to a volume of 55 cubic decimeters. When 1.10 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. This is not a straightforward one. I'm going to think about this. Okay, scale model of a blimp. So we've got this blimp. Kind of looks like a fish. We want it to rise. It will rise when the volume is 55.0 cubic decimeters. Now that's a unit of volume that we don't use very much, but that's okay. Let's not do any converting unless we have to. So that's what we're trying to get. There. That's the balloon rising. So now we've got our blimp down here, and it's just kind of deflated. So we're adding 1.10 moles to the assumingly empty blimp, moles of helium, and that causes the volume to be 26.2 cubic decimeters. And so we want it to be this volume. Well, let's put these numbers into a table and see if we can do anything with that. These two go together, so I'm gonna do those first. We've got 1.10 moles, and that would be N. That's the amount of gas in the blimp, and 26.2 cubic decimeters. That's the volume. We want to know how much helium we have to add to get to this volume. So we've got a table there of N's and V's, and we could find out what N2 is. Is that the amount of helium in grams that we need to add? No. That's the amount of helium in the balloon in moles that we need to get to. So that's partway to our answer, and then we're going to have to do some other calculations. V1 over N1 equals V2 over N2. We're solving for N2. N2 is V2 N1 over V1. So what did I do there? I took the N2, I put it up here, I put the V1 down there, and I put the N1 up there. If you want to see that all written out, ask me after, and I'll do it for you. So volume 2 is 55.0 cubic decimeters. N1 is 1.10 moles. Divided by volume 1, 26.0 cubic decimeters. The cubic decimeters cancel out, and we're rid of that unpleasant unit. So 55 times 1.1 divided by 26.2. I didn't do that very well. 0.2 gives me an answer of 2.30916. That should have 3 sig figs, moles. This is the amount of helium that needs to be in there for it to float. So 2.31 moles. Everybody okay with that? So this is what I have. This is what I want. The question is asking, how much helium do I have to add to get there? So I can figure that out in moles by subtracting 2.31 minus 1.10 is 1.21 moles. I need to add 1.21 moles. How many grams is that? Well, this is helium. 1.21 moles of helium times the molar mass. So that's just on the periodic table. 1 mole is 4.003 grams. Are you going to stop me? I got it upside down, right? Look at this. Moles times moles over grams. What? Yeah, that's wrong. Say, oh, shoot, that was dumb. Okay, we'll fix it. I want moles in the bottom and grams on top. It's 4.003 grams per mole. So 1.21 times 4.003. So 4.84 grams of helium. Okay? This part is just learning how to solve a particular kind of problem. And you can make a table and you rearrange the equation, you plug the numbers in. That's all lovely. But we also have to be able to think about it and apply it to a situation that we haven't seen before. I won't give you one just like this on an exam. I'll give you a different one that wasn't in the homework, it wasn't in the book, you've never seen it before. But you have all the pieces and you should be able to put them together. Any questions? Yeah. So 2.31 is the amount of helium that needs to be in there at the end. It tells me I already have 1.1 moles. And the question's saying, what mass do you have to add? So if I take what I want to have and I subtract what's already in there, that gives me the amount in moles that I need to add. And then I convert that to grams. Any other questions?